Hello everyone. So we said that to find the area between the curve y equals f of x and the x-axis, all we have to do is just integrate y with respect to x. So we just do the definite integral. But how about if we have to find the area between curves? So let's see how to handle that in this video. So firstly, in the first video, we'll look at curves which are defined with y in terms of x, and then later we'll look at curves that are represented with x in terms of y. But let's suppose we have a region that's bounded by two curves, y equals f of x and y equals g of x, and the lines x equals a, x equals b on the left and right. And let's first suppose that f is bigger than or equal to g on AB. So there is a top curve and a bottom curve, and the top curve always stays on top and the bottom curve always stays on the bottom. Then how do we find the area between them? Well, all we have to do is just do the integral of the top curve minus the bottom curve. So we just have to integrate from a to b f of x minus g of x. So this is going to be an integral of something in terms of x. As soon as we figure out what the integral should be, we just use that antiderivatives, use the fundamental theorem of calculus, plug in a, plug in b, and subtract them. So let's see why this is true, and then let's do a quick example. So we're going to integrate top curve minus bottom curve. So here is two curves, f of x and g of x, and just for the sake of it, I put g to be, so always f is going to be bigger than g here, but just for the picture, I made f above the axis and g below the axis, so you could draw a similar picture if that wasn't the case, if they had different positions. But okay, let's remember how we define the area between the curve f and the x-axis. We split the interval AB up into a bunch of little pieces. On each of those little pieces, we approximated by a rectangle. We added up the areas of the rectangles, and then we took the limit to get the area. And now we're basically doing the same thing, right? So we chop up into all these pieces, xi minus 1 to xi, and we pick the sample points, xi star in between, just like we did before. And now we have a rectangle, and there's going to be a top and a bottom of a rectangle. So we choose the height on the top part of the rectangle to be the value of f at xi star. So here is f of xi star. And then we choose the value of the height on the bottom of the rectangle to be this distance to the curve g. And here, because g is negative, the distance to the curve g has to be positive. It's going to be minus g of xi star. So if the curves are in this position, we have a rectangle. This piece is f of xi star in height. This piece is minus g of xi star in height because g was assumed to be negative. So we should add up the areas of these rectangles and take a limit. So here is the area of the rectangle. The area is f plus minus g, so f minus g. So that's the height. And then the width is delta x. And then so this is the area of one rectangle, and then we add up the areas of all the different rectangles to get an estimate for the area, and then we take a limit. So it looks pretty complicated, but fortunately we can recognize that this is just the definition of the integral with the function replaced by f minus g. Right, so normally here we would have f of xi star times delta x, sum, and then take the limit. Here we have f of xi star minus g of xi star. It's just the same as the definition of the integral, but with f replaced by f minus g. So what we're going to get instead the integral of f minus g. So that's exactly what we said right in the formula. Okay, so let's see how this works in an example. So let's try to find the area bounded by y equals e to the x and y equals x, and bounded on the left by x equals 0, on the right by x equals 1. And we said we should have a top curve and a bottom curve. So which curve is bigger in this case? So in this case, e to the x is going to be bigger or equal to x for x between 0 and 1. For instance, if you sub in x equals 0, e to the x is going to be 1, x is going to be 0. If you sub in x equals 1, e to the x is going to be e, which is 2 point something. X is going to be 1, which is smaller. So naturally, across this interval, e to the x is bigger. So we have to integrate top curve minus bottom curve. So now we can say the top curve is e to the x. So we're going to be integrating e to the x minus x from 0 to 1. And now once we set this integral up, it's something we already know how to do, right? We just find the antiderivative, we plug in 0, we plug in 1 and subtract them. In the end, we get e minus 3 over 2. Okay, so if one of the curves stays on top, then it's relatively straightforward. Okay, so what about if, so here in this example, we had the sides a and b specified. So we were told x equals 0 and x equals 1. If they're not specified, then it's going to be kind of like before when we had to solve for where the curve intersects the axis. In this case, to find the a and b, we're going to have to solve to see where the curves intersect. So here, for instance, the curves can intersect themselves and form a region without us specifying those lines x equals a and x equals b. And to find these 2 points where we're supposed to start and end, we have to solve where the curves agree, so where they intersect. So let's see that. For instance, let's find the area of the region enclosed by y equals x squared and y equals 2x minus x squared. So if we see that they're enclosed by a curve and there are no x equals a and x equals b specified, then it's pretty likely that the curves are going to intersect, or they're going to have to intersect to form a region. So we look for the intersection points. So we set x squared equals 2x minus x squared, or if we solve then for x, we bring everything over, we get 2x squared minus 2x equals 0. we can factorize. It's going to be 2x times x minus 1 is equal to 0. So we're going to have two solutions, x equals 0 for when the first factor is 0, and x equals 1 for when the second factor is 0. So these are our two x values. And do be careful, as always, when you're solving equations, right? If you say here you were to cancel an x, if you cancel the x, remember you're probably losing a solution x equals 0. So you have to check that's also a solution. Okay, so we have two solutions, and then we have to figure out what is the top curve, what is the bottom curve, because we're supposed to integrate top minus bottom. So here, for instance, if x is between 0 and 1, we could plug in a half to see, a midpoint to see which curve is on top. So if we do that for y equals 2x minus x squared, we will get 2 times a half, which is 1, minus a quarter, we will get 3/4. Whereas if we plug a half into x squared, we will get 1/4. So the value of the first curve would be bigger than the value of the second curve, so the first curve is going to be on top. Okay, so now we figured out where the region starts, where the region ends, which curve is the top, which curve is the bottom. We can set up our integral. It's the integral from 0 to 1 of the top curve, which is 2x minus x squared, minus the bottom curve, which is x squared. Okay, we can rearrange, and then we do some algebra using the power rule. Use the power rule to integrate, plug in the endpoints. In the end, we'll get 1/3. So there's nothing new apart from figuring out what integral exactly we're supposed to do, right? Figuring the endpoints, figuring the top and the bottom. Okay, but what about if the curve which is on top changes throughout the interval? So in that case, we should split up and just find the area of each piece separately. So for instance, suppose at the start, the f is on top and g is below, and then later on g is above and f is below. Well, we should split up into two pieces, on each of which integrate the top curve minus the bottom curve. And there is a shorter way to write that in a formula. It's the same thing as integrating the absolute value of f minus g. So in general, you can always integrate absolute value f minus g, and this is equivalent. Remember, we said that to integrate absolute values, you should figure out whether inside is positive or negative. If it's positive, you can just delete the absolute value. If it's negative, you swap the sign. If it varies, you break it up into a chunk of pieces and handle each one separately. That's the same as what I just said with with splitting up and integrating top curve minus bottom on each case. So it's up to you how you want to think about it. So let's see that in an example. So let's find the area of the region that's bounded by y equals sine x and y equals cosine x, and x equals 0 and x equals pi over 2. Okay, so here's our region. We have x equals 0 on the left, we have x equals pi over 2 on the right, and then we have this region on the left and this region on the right. It's bounded by the different curves. And on one of the sides, cosine x is on top, and the other side, sine x is on top. So we should break up the integral that we're going to do into a bunch of pieces, on each of which integrate top minus bottom. So let's see where we have to break it. So the top and the bottom curve can switch when the curves intersect. So here I wrote on the pi over 4 as the intersection point. Well, let's see why that's true. Well, they intersect when sine x equals cosine x. That's the same thing as saying tan x equals 1, which has the solution x equals pi over 4. And there are other solutions, but no other solutions in the interval from 0 to pi over 2, which is what we're interested in. So the only time they intersect between 0 and pi over 2 is at pi over 4. And then we have to break up from 0 to pi over 4, from pi over 4 to pi over 2, and on each interval think which curve is on top. For instance, if we go from 0 to pi over 4, sine of 0 is 0, and cosine of 0 is 1, so the cosine curve is going to be on top. And if we go from pi over 4, sorry, here should be pi over 4 to pi over 2. If we go from pi over 4 to pi over 2, for instance, at the pi over 2 endpoint, sine of pi over 2 is 1, cosine pi over 2 is 0. So in the second part, the sine curve is going to be on top. So we said we should split into two pieces, on each of which integrate top minus bottom. So on the first one, we're going to integrate cosine minus sine. On the second, we're going to integrate sine minus cosine. Okay, or we can think of it as this formula. So let's go ahead and do that. So in general, it's the integral of the absolute value. So sorry, here from 0 to pi over 2. So we are going to go from 0 to pi over 4 and do the top minus the bottom. So we have cosine minus sine. And then on the second piece, we are going to have pi over 4 to pi over 2, and we integrate the top curve minus the bottom. On that piece, it's sine minus cosine. Okay, and then now that we got rid of the absolute values, we can just use our antiderivatives and the fundamental theorem of calculus, plug in the endpoints, and in the end you will get 2√2. Okay, so just to summarize, we said that to find the area between curves, we should integrate top curve minus bottom curve. And sometimes the curves intersect and make a region without us specifying x equals a and x equals b. In that case, we have to solve to find the intersection points. And if the top and the bottom curve vary, then we should split into pieces, on each of which there is one top curve and one bottom curve, and do those separately. Okay, thanks everyone. See you next time.